I'd argue that one of the most mysterious parts of the Milky Way and many other spiral galaxies in the universe is their bars and how they work. I mean, it's only very recently within the history of astronomy that we've even been able to very decisively confirm that the Milky Way has its own bar. But at first glance, it is quite odd that bars exist in the first place. I mean, gravity and the universe tends to prefer very spherical structures, albeit somewhat slightly flattened at times. So why do we have such a very rectangular structure in the centre of many spiral galaxies? Today we're going to be focusing on exactly that. We'll be looking at the bar, how they form, and how they evolve over time. Hi, I'm Seti. I'm a PhD student studying galactic dynamics, mainly focusing on the Milky Way, but looking at other spirals in general, and that does include at times the bar and bar formation mechanisms. My channel is mainly focused on astrophysics and covering all the weird and wonderful aspects of space, such as bars, spirals, galaxies in general, supermassive black holes, planets, you name it. I will probably make a video on it at some point. If you're interested in astrophysics, I highly recommend you subscribe. It helps me out and it also helps you out because you get more space-themed content. I try to make videos every 2 weeks, plus minus a couple given how busy my schedule is as a PhD student. But in general, I try and keep to that, and I really hope that you can learn something from my videos. There are 3 main parts of the galaxy. The bulge, which is in the centre and makes a fairly small proportion of the total mass. We've got the disk, which extends out for much larger radii and also is where most of the fun happens with spiral galaxies. I mean, that's where the spirals are, and we also get fun things like warps and tilts and whatnot. We've also got the halo, which is for the most part, fairly spherical structure that encloses the disk and the bulge within it. Today we're only really going to be focusing on the first one, the bulge. The latter 2 we won't be looking at today. The reason why the bulge is important is because at least half of all observed spiral galaxies as bulges will take on the form of a bar shape. So I feel like that's reason enough to study them in detail. The Milky Way's own centre is very well characterised by a boxy or peanut-shaped bar, with estimates for its length ranging between roughly 3 to 5 kiloparsecs. In general, star formation is quite limited within the bar and the bulge in general. Most of it is concentrated at the tips of a bar, and that's because you get a lot of compression of gas at the ends of the bar, and so that compression of gas can allow for more star formation to happen, basically. So with the limited amount of new young blue giant stars populating the bar, in general, most bars take on a very yellowish appearance, where it's mainly dominated by slightly older stars. Spectroscopic studies of the bar show that there is quite a big variety in stars, albeit not that many young ones, as I have just said. A very recent paper that I read by Xiao Han et al. Was able to split up the stellar populations into 3 big subgroups, one of which actually being halo stars that are just visiting very briefly, so I thought that was interesting and I hadn't considered that before. But they showed that you could fairly easily see these differentiations of subgroups based on the eccentricity of their orbits, but also to a lesser degree their metallicity. However, in general, you can pretty much split up the stellar population within the bar by pretty much any metric you want. It's quite a very varied place. You can do metal rich, metal poor, depending on their orbits and their kinematics, for example, or even other things like the actual types of stars, because you have quite a big variety of them as well, such as red clumps or RR Lyrae. I mean, it's a very cosmopolitan place. Going back to the tips of the bars, a sizable proportion of barred galaxies will actually have these very odd handles at the ends. Formally speaking, they're usually referred to as Ansai type bars, so if you want to search it up, that's the sort of terminology that you'd want to use. Although we don't really know why they arise. The only thing that I can really conclusively say is that they're more common in these yellower or early type spiral galaxies, but in general we don't really know what mechanism is driving these. So now that we've got a basic understanding of what the bar is made up of material-wise, I think the next question we should ask is what actually is the bar made up of? Like, how do those stars get those really weird orbits that would then go on to form the bar? Thankfully, that answer was found quite a while ago We have a range of families that support the shape of the bar, but the biggest contributor is what we call the X1 family of orbits. These are basically just lemon-shaped orbits that look like circles that have sort of been pinched out and elongated. It's actually quite difficult to get access to some of these papers that focus on the X1 orbits of the bar online, mainly because my university doesn't give me access to like the vast majority of papers and science journals online, which is stupid, and as a member of the public, I'm gonna assume that you won't be able to either. However, I did find and read this this paper that was released a couple months ago that was focusing on simulating the central molecular zone of the Milky Way, and which is more concerned with the X2 family of orbits, but as a natural consequence they have to also look at the X1 family as well, so they had some really good figures that I want to talk about. Right, so this paper, as I said, was by Chavez Velasquez et al. It was more concerned about the innermost regions of the Milky Way, namely the central molecular zone. Now, this is an interesting area of the Milky Way because it has a lot of molecular gas at really high densities, and yet it doesn't really have much star formation at all. So it's quite unique in that that doesn't really occur in the rest of the galaxy, where you get high compression gas, you get a lot of star formation, but it's quite the opposite here. So figure 4 is the first one I wanted to talk about, and I will pop it on the screen, but my screen is right down there where I'm going to be looking at the figure and describing it, so excuse me for not looking directly at the camera here. But I really liked figure 4 because it is basically a bird's eye view of both the X1 family of orbits and the X2, and you can pretty clearly pick out which one's which. So you can see here where we've got basically we've got both the orbits which are on a colour mesh. So where we've got areas that are very red and yellow are areas where you have a really high gas density here, which is what they've represented. And then areas that are very low gas density, you have basically the lilac-y white colours. And so you can see overall the X1 family is mostly in a very lilac sort of colour. So it's fairly lowish gas density, but relative to the actual background, it is actually quite high. But then you can see at the tips of these X1 orbits is where you get a slightly even higher increased rates of increased gas density, which is where we see the compression and the star formation happening. So that matches up pretty nicely to real life. On top of that, you've also got another set of orbits that are slightly smaller, and they're oriented slightly 90 degrees to the X1 family of orbits, and these are the X2s. Now, these are not actually all that important in holding up the bar and stabilizing it, so I won't focus on them too much, but you can actually see that they are a lot higher in gas density compared to the X1 family of orbits. So yeah, the X1 family of orbits are the main contributors to holding up the bar. They are aligned with the bar, so where it actually pinches out are the tips of the bar, whereas with the X2 orbits, as we've just seen, it's actually the opposite, so they're shifted perpendicular to it. So they don't actually do that much when it comes to holding up the bar. What we think happens when it comes to formation of bars is that there is some small instability of the disk that triggers it. Namely, for example, a non-even density in the disk or the bulge. A change in density will naturally affect the gravitational potential of a disk galaxy because you are redistributing the mass. Hence, something like this can very easily guide stars into these really odd orbits, which will end up having stabilizing effects that will then keep a bar long-lived and, just going. And this kind of makes sense if you think about it. We see that a small majority of barred galaxies, or disk galaxies actually, have bars, and it seems that they're all very long-lived as well and can last a few billion years. So you can't really have a very peculiar circumstance or require a really large instability to actually trigger the bar. It needs to be something that's quite long-lived or quite easy to trigger. I personally think we should informally call the X1 orbits lemon-shaped orbits or lemon orbits, and that's mainly because the next set of orbits are also going to be named after foods, namely the banana orbits, and deviating from the fruit analogy, we also have the pretzel orbits. These are really important, not necessarily for actually stabilizing the bar and allowing it to be long-lived, but to actually thicken it out into the boxy X-shaped or peanut-shaped bar that we actually observe. It's quite difficult to observe individual orbits, mainly because, it would take a few million years, first of all, And of course, we're obscured by being within our own galaxy. So we do rely heavily on simulations to show us this fine detail. And for this, I really recommend this paper called Peanuts, Pretzels and Bananas, Food for Thought on the Orbital Structure of the Galactic Bulge by Portail et al. It's a really nice paper. It's quite short as well, but it has quite a few good figures as well, which will really help understand sort of the nature of these orbits. They found in this paper that you could pretty effectively model the bar as just a superposition of peanuts produced by various orbits. In the general literature, we typically assume these to be mostly banana-shaped orbits, so these are orbits that aren't actually flat in the disk's plane in the XY, but they actually lift up at the ends of the orbits here. So they have a little bit of vertical height due to some vertical resonances within the actual disk itself and the bulge, in the galaxy in general. So this would make sense if you have a bunch of different orbits that are lifting up or lifting down or around, and so that would eventually just thicken out the ends of the bar more than the center and sort of create that very peanut-shaped bar. However, they argue something slightly different. But Portail et al. In this paper actually argued that a bigger portion of these orbits actually have to be shaped like pretzels. And this is basically very much a question of how much is the bar shaped like a peanut compared to shaped like an X or a box. So in the more recent literature, we're more so arguing that the bar is more shaped like an X rather than a peanut, and so that would mean that these pretzel-shaped orbits would play a much bigger role in actually creating the 3D shape of the disk. So why do we even care about a bar if it's so restricted to the center of the galaxy and is super distant and far away from the outermost regions where all the fun happens, in my opinion? Well, they are still in communication with each other, of course. Small changes or big changes in the bar can definitely influence the outermost regions of the galaxy. And not only that, a vertical, very strong bar can, of course, induce very small spiral arms as well, mainly because it is a non-axisymmetric perturbation within the potential of a galaxy, so naturally it can cause these if strong enough. And not only that, but the bar is very vital for transfer of angular momentum between the disk and the bulge, and also gas flow as well between both sections of the galaxy. So it is really vital in, reshaping the disk, so I think it's quite important. But there are many unknowns regarding the bar in our own galaxy. First of all, it is expected that the stars in this bar will rotate rigidly with an angular frequency that we usually call the pattern speed of the bar, and we expect it to gradually decrease over time. So basically, the bar rotates as one big thing with a pattern speed, and that should slow down over time. A really good estimate of the pattern speed can open up some really good areas of exploration into the kinematics of the galaxy. And it allows us to really accurately identify resonant radii within the Milky Way, which in turn lets us explore the bar's effects on the greater stellar population. So while it is quite important, unfortunately, pattern speed estimates for the Milky Way are really difficult to get a hold of, mainly because of our problems with our observational perspective, given that we are actually inside our own galaxy and it's very difficult to observe. And of course, we've got some really large timescales involved. So if you want to look at how fast the bar rotates, you can't really look at an entire revolution and, go from there. It would be impossible. So we use other methods of interpreting the pattern speed, mainly things like using the Jacobi integrals, moments of inertia, or basic Fourier decomposition. I say basic, it's definitely not. But in general, pattern speed estimates can range between roughly 31 to 45 kilometers per second per kiloparsec, which is actually quite a big range. And not only that, we also need to consider the effects of any statistical errors. So, for example, if we want to get these estimates from stars that are within the bar or within the bulge or the center of the galaxy, it can really greatly affect our results whether we take estimates from stars that are in front of the supermassive black hole or stars that are behind the supermassive black hole, because of course having a central engine is kind of a big obscuration. Pattern speeds are also important because they carry information on the relative size of the bar. High pattern speeds suggest that the bar is rotating very quickly but is also quite short, and then a small pattern speed would indicate that the bar is quite long but quite slowly rotating. So to conclude, we've covered pretty much the basics of the bar and the bar within the Milky Way, its formation, and the type of orbits that are expected to support the bar structure in both 2D and 3D, sorry. These are mainly the X1 orbits that we covered, which are the lemon-shaped ones, but we also need to consider banana orbits and pretzel orbits. Bars are a sign of a very highly structured and evolved galaxy, and they're really important for angular momentum transfer and gas flow between the disk and the bulge, so they are a really interesting point that we need to research better within galaxies. That being said, there are quite a few unknowns regarding the bar in our own Milky Way, namely the pattern speed, so how fast it rotates, and also its length as well. These are really important in order for us to really, explore the kinematics within the galaxy. But in time, with better observations and improvements to our simulations, we should be able to better constrain these sort of concepts and parameters much better. I think that pretty much summarizes everything we've talked about and most of the basics of the bar. In the description section below, I will leave you both the paper that I talked about by Portela et al., the paper by Chavez Velasquez et al., and also I'm going to leave you with a website which was made by Ronald J. Buta, which talks about galaxy morphologies and the bar in a lot more detail. And it is honestly an absolutely fantastic resource which has really helped me in better understanding bar formation and just bars in general, because there is so much regarding them that it's just impossible to all cover within one video. If you like this video, I highly recommend you watch my galaxy classification video where we talk about a lot more aspects of just all types of galaxies, so ellipticals, lenticulars, spirals, barred spirals, irregulars, and we break down all the different classification systems as well. I also have another video in my galaxy review series where we talk about the warps in the outer disk of the galaxy, which I also highly recommend you watch. And in general, if you like my content and you're interested in astrophysics, I do recommend you subscribe. And with that being said, I'll see you in the next video.